Hello, you've joined Titanic and Beyond, a Woods Hole Oceanographic Institution Ocean Encounters presentation. We have a lot of people joining us tonight, so please bear with us. We'll get started very shortly. And now, please take a moment to read WHOI's land acknowledgement.
The ocean covers 70% of the globe. It gives us oxygen and food and millions of jobs. It brings joy and shapes our climate and weather. The ocean is life, and it belongs to everyone. Woods Hole Oceanographic Institution is the world's independent leader in ocean discovery, exploration, and education, working to understand and sustain one of humanity's most precious common resources. Join us today for our ocean, our planet, and our future.
Welcome to Ocean Encounters, a virtual series from Woods Hole Oceanographic Institution, or WHOI, as we like to call it for short. Tonight's event is Titanic and Beyond, the evolution and impact of deep sea imaging. My name is Veronique LaCapra. I'm the host of Ocean Encounters. WHOI's public event series is in its 7th season and is an endorsed activity of the UN Decade of Ocean Science for Sustainable Development. If you've tuned in before, thank you for watching. And if you're new to Ocean Encounters, welcome. I'd especially like to thank any WHOI members who are joining us tonight. You are the heroes at the heart of our efforts. Before I introduce our speakers, I want to let our Zoom audience know they can participate in tonight's live conversation. If you have a question for one of our panelists, please use the Q&A button on your Zoom screen and type your question in the window that appears. You might be more used to the chat function in Zoom, but tonight, please ask your questions using the Q&A button instead. We often get hundreds of questions, and I'm sure tonight will be no different. So I apologize if we don't get to yours while we're live. You can ask questions anytime, starting now. I'd also like to remind our Zoom viewers that Ocean Encounters now has live American Sign Language interpretation. To enable the ASL feature, please click on the interpretation button at the bottom of your Zoom screen. We're also recording this event, and that recording will be made available on the WHOI.edu website. We had more than 2,260 people pre-register to join us tonight, so you are in very good company. We also have viewers joining us right now on Facebook and on YouTube. To everyone, thank you and welcome. Let's get started. Just after 1 a.m. on September 1st, 1985, a joint WHOI-French expedition discovered the wreckage of the Titanic. To do it, they towed cameras recording grainy black and white film more than 2 miles below the surface for days. Imaging technology has come a long way since that historic event, bringing breathtaking discoveries from the deep ocean and outer space right to our homes. Let's bring on the first of our panelists, Stewart Harris. Stu is a retired UC Berkeley aerospace engineer, and he was also a lead engineer on that momentous Titanic expedition. Welcome, Stu.
Hi, Veronique. It's nice to be with you.
Great to have you here with us. Stu, you recently retired from a long and very successful career in aerospace engineering. Congratulations. But as I mentioned, early in your career, when you were about 30 years old, you were hired out of aerospace by Bob Ballard, who may be a familiar name to many, to come and work at WHOI. And Bob asked you to design and build a vehicle that went on to play a leading role in the discovery of the wreck of the Titanic. The vehicle was called Argo. Please describe it for our audience.
Well, Argo is a towed vehicle. It's 16 feet long, weighs over 2,000 pounds. This photograph was taken on the Woods Hole dock. That's me with my back to the camera. It's maneuvered near the bottom, suspended by a tow cable, such that it trails along behind the ship. This cable is a steel armor coax cable and on that single conductor, we transmit power to the electronics on the vehicle, and it provides a limited uplink bandwidth for analog data. There were 3 cameras mounted in the front of the vehicle. These were low light level cameras. There was also a film camera such that we could take photographic stills. There were floodlights and strobe lights mounted in the back of the vehicle to provide illumination for those visual sensors. But we also had acoustic sensors. There was a side-looking sonar system on board that would look to left and right, or port and starboard. And there was an altimeter to tell us how high off the bottom we were. But Argo was operated from a control room that was on the deck of the ship. This was comprised of 2 shipping containers. You can see here a photo of us loading that container on the ship. And it was from there that we viewed the data while searching for the Titanic. That's where we lived during the search. Here's a shot inside the control room during an operation. And so the fellow with the beard sitting down at the console is the Argo operator. And that's Bob standing there looking heroic while he's being filmed.
All right. Okay. So Argo might sound a little basic to us today, but in the early 1980s, it was actually a real innovation. What was sort of the status of ocean imaging at that point? What had come before, and what made Argo different?
Well, Bob and his deputy Skip Marquet had started the Deep Submergence Lab in the early 80s, and it was at DSL that we built Argo. Their previous experience was using the manned submarine Alvin for seafloor exploration. But it was Bob's vision to supplant the manned submersible by using remotely operated vehicles like Argo, because you could operate them 24 hours a day instead of being limited to the 1 dive per day that you could do with Alvin. Argo was based somewhat on an earlier towed sled called Angus. Angus was a vehicle with a towed sled that was equipped with high capacity film cameras and strobe lights and operated with batteries. So it was used to assist Alvin operations by scouting out sites for future Alvin dives. But Angus was also sometimes called dope on a rope because it didn't provide any real-time images of the bottom. It was towed on a course and was strictly taking film in the blind. Live TV of the seafloor, that was the innovation of Argo.
Yeah, so with Angus, the predecessor to Argo, when you talked about it shooting film, and you're really talking about, the kind of film that would need to be developed in a darkroom on the ship.
That's right. Yeah. So there was a film processing lab on board. It was also installed in a shipping container, so it could be shipped around easily. But that was a key part of the Angus operation. That the vehicle be brought up on deck, the film would be unloaded from the vehicle, taken in that lab, and immediately processed. And then you could view it with a strip projector, film strip projector.
Yeah. But so with Argo, you could actually get shots in real time of what you were passing over
That's right. You were viewing the seafloor in real time as we were traveling over.
Okay. So with that context, let's talk about the Titanic discovery. It's the late summer of 1985. The expedition, as I said, was a joint mission between French researchers and WHOI researchers. And the French were out searching first. We actually have a clip of Bob Ballard talking about how the two teams approached the search. Let's take a look at that.
Our tactic, being a visual tactic, is going to be quite different than their acoustic tactic. You go with your sensor. Ours is a visual imaging sensor, and we're going to be looking for debris. We have various material that gives you a historic account of the ship, but a lot of stuff went in the water as that ship sank. At least the two of us believe the boilers probably went through the bow and bombardier into the bottom, and that they would have brought a tremendous amount of debris with them because the mail room, supplies, everything was up in the bow, and it would have just taken that out. So it should have introduced a lot of material into the water.
Okay, so let's dig into that a little bit. So the French were out there using acoustic sonar, and they were looking for the actual wreck of the ship. WHOI was doing something a little different. So talk more about that.
Well, so that Bob and the French leader, Jean-Louis Michel, Jean-Louis is the fellow on the far left in the image that you're looking at right now. Of course, Bob is second from the right. So our French colleagues joined us for the American portion of this. But Jean-Louis and Bob had defined a search area. It was about 100 square miles in extent. And the French arrived out on scene in their ship, the WHOI, and with their side-looking sonar system, which they called SAR, and they proceeded to investigate this area. So what's on your screen right now is that search area. The area that's shaded pink is the area covered by the French side-looking sonar, and the first search area is outlined in a dashed line, and you can see they covered a large portion of it, and it was about 80% of that initial search area. But and they did identify a few targets of interest, but nothing definitive. And so we arrived on scene with Argo. Argo had been funded by the Office of Naval Research, and they were funding the operation, the cruise itself. But we arrived on scene in late August. We only had 10 or 12 days of ship time remaining for our portion of the search. And, given the sort of negative results of the French effort, that's what really demanded a change in tactics. The Bob and Jean-Louis estimated that the footprint of the debris field was probably a mile in extent, which is that's a much bigger target than just the physical wreckage. And so our idea, or their idea, was to search for the debris field, not the target itself.
And when you say the debris field, you're talking about smaller bits of debris that would have broken off. And
that's right. So these are pots and pans and lines and piping and that sort of thing. And so our track lines, which are shown here in light blue for Argo, were spaced a mile apart. And I mean, when we initially arrived on scene, we actually did go and visit some of the potential targets that the French had identified, but they just turned out to be natural features. But so then we started our regular search pattern that's shown here in this graphic. And it was that technique that led us to the wreck, because we found the debris field and then just zeroed in on where the main pieces of the wreck were.
Okay, so let's hear that story. You're on site, time is running out. Argo, the vehicle you created, is in the water. You're its lead engineer on the expedition. Take us to those early morning hours of September 1st, 1985.
Well, this is the scene inside the van. That's me actually sitting in the Argo operator position. We stood a regular schedule of watches, 4 hours on, 8 hours off. There were 7 of us on watch at any one time. So we were working. So each of us, stood 2 watches per day, working 24 hours a day. And these were days of watching gray, featureless seafloor rolling along past us on the every day. Just your goal was to watch the monitor and identify anything that we would see. So the challenge was just to stay awake and stay alert most of the time. But on September 1st, I was on watch 4 a.m. I'm sorry, the midnight to 4 a.m. watch. And a little after 1 a.m., we started seeing some debris. Initially, it was just small stuff, very sparsely located. And then not long after that, we started seeing some real major things like what you see on your screen here, real twisted pieces of wreckage. And clearly everyone started getting very excited at that point. I famously yelled bingo. And it was about then also someone remarked that somebody needs to go wake up Bob. So fortunately, one of the cooks stuck his head in the van about that time, and we convinced him to go wake up Bob. And I think he actually probably woke up everybody on the ship at that point. But because no one wanted to leave. I mean, and it was actually right then that we ran over and saw the image that you're seeing right now on the screen, which just nailed it for everyone. This was a shot of the boiler, or one of the Titanic boilers sitting on the bottom. And we knew exactly what it was because we had this great photograph of looking down the line of boilers in the belly of the Titanic. And you can see they have this distinctive bolt pattern on them. And so when we saw that fuzzy image of the boiler, we knew exactly what it was. And it was as positive an identification of the Titanic as seeing the Titanic nameplate on the stern of the vessel. It was absolutely what nailed it for us. And it was actually only a few hours later that we found the main pieces of the wreckage. I mean, as you might know, that it broke into two, the ship broke into two as it sank. And then there are two main pieces of the wreck as they are today, which is the stern section and the bow section. And they were both located within the original search area, just right on the eastern border of it.
Yeah, the French had actually come very close.
They just missed it. They had just missed it.
Yeah, so it's those two little black dots right at the end there of the blue track, right, just outside of the pink portion.
That's right.
Yep. Such an amazing experience for a young engineer, I must say.
Yep.
And there's the whole team on the ship. I have so many more questions, but I bet our audience does too. So let's find out. My colleague Ken Costell is, as always, behind the scenes monitoring the Q&A. Ken, do you have any questions for Stu?
Yeah, they're coming in faster and faster. We were in rehearsal, we were saying we thought somebody might notice this, and sure enough, one of our eagle-eyed viewers saw that Stu has a background in aerospace engineering and wondered, how did that inform his work on Argo and further on imaging in the deep ocean?
Great question.
Yeah, well, before coming to Woods Hole, I had worked at Lockheed in Palo Alto, California, and we were building low light level cameras for observing aurora from space. And so I was very familiar with the technology of the cameras used on Argo. There are these silicon intensified target, or SIT cameras, as they were known, which is a tube type technology. It was an early generation of night vision technology, and very similar to the cameras used by the Apollo missions on the moon. So it's those cameras that allow you to operate at a somewhat higher altitude over the bottom with the illumination provided by the floodlights. So that was having that background was made it very simple for me to transition into the ocean environment.
Yeah, and then I think you went on to develop another type of of camera.
That's true. After the Titanic expedition, came back to Woods Hole, and I worked on developing a what we called an electronic still camera that was based on cooled CCD technology. And this was now more of a digital format than the tube type analog cameras. And these cameras, we illuminated the images with strobe lights, so which is a much higher intensity light. And so they produce snapshots, but we had a sensitivity really comparable to the SIT cameras, but with a much higher fidelity image quality that allowed you to see through the fog of the underwater imaging.
And were those something you had worked on at Lockheed as well?
Well, it was a direct spinoff, really. It was cameras used for astronomical uses from outer space. So they're known to have a very wide dynamic range, which means they have a lot of bits per pixel, and you can really pull out detail in the image that way.
Okay. Ken, any more questions?
Yeah. Casey was wondering, why could Angus only do one dive a day?
Oh, it wasn't Angus, it was Alvin. So Alvin, the limitation is both human and electrical, in that you're putting three humans inside the sphere, and they have to go down and dive. It's to the deep ocean depths. It can be a 2-hour elevator ride to get down to the seafloor and then to come back up, and then however long you can withstand your time on the bottom. So it's really how long can the humans, withstand that sort of enclosed atmosphere. Plus, you have to bring the submarine back up and recharge its batteries. So you really can only physically do one dive a day with Alvin. Angus was battery operated, and it was actually used in conjunction with Alvin. They ran Angus or operations at night while Alvin was on deck being recharged.
All right. One more Titanic question, and then we're going to move on.
We actually have a question from the grandson of a survivor.
My.
And this is sort of maybe a just philosophical question. And he says he means no disrespect in asking this, but why, he wonders, has the Titanic become such an object of curiosity, when it is the resting place of so many souls?
That is a really good question. And it's one that I am sorely unprepared to answer. I've often wondered it myself. There's a multiple reasons. There were many famous people who were on the Titanic and were lost at sea. And people have a real fascination with celebrities. That's one answer. And it was, the discovery of the wreckage was a big news-making thing, garnered a lot of attention. Again, it was for a few hours we were all celebrities, and so that's another factor. But it's you're asking a question that it could probably be better answered by a philosopher rather than this techno geek that I am.
Yeah, but I do
it's a great question.
I want to thank that person for reminding us that the Titanic was a horrible tragedy, and will always be that. We're talking about the science of imaging today, but we don't want to forget the people, the many people who lost their lives.
That's true. Absolutely.
Okay, so we're going to move on now from Titanic. At the end of tonight's show, we will share a video of the Titanic discovery that Stu just described. So please stay with us for that. Now I'd like to bring our other two panelists into the conversation. They are WHOI Ocean Exploration and Imaging Technologist Dwight Coleman and Olin College of Engineering and WHOI Field Roboticist Victoria Preston. Welcome, Dwight and Victoria.
Thank you. Great to be here.
All right. I'd like to fast forward now from the 1980s to the present and talk about what deep ocean imaging can do today. First, Dwight, what are some of the big ways that imaging technology has evolved since that Titanic expedition?
Yeah, wow. I wish we had more time because there's a lot of different ways. But just quickly, from what Stu described from the Argo vehicle 40 years ago, we did, it was quite advanced to have that real-time connectivity to the video and look at the seafloor in real time. Of course, now we're using fiber optics on the cable, and we can get the data transmitted even faster up to the surface. And we can use the network technology of fiber optics to add a control feature to it. So we can, for example, zoom and focus the cameras as the data is coming in and collect even higher quality images than we could before. And of course, this digital revolution has really changed camera technology and the data and the imaging data that the cameras collect, of course, and we're able to collect much larger volumes of data. High definition video came around, and underwater cameras were built about 25 years ago, and now we have 4 times that, or 4K cameras, and even up to 16K technology, 16 times the quality or the resolution or definition of high def that we're all used to. Improvements to deep sea lighting, LEDs now are the new technology that we're using that is a much more powerful and energy efficient means to illuminate the area that we're looking at. Of course, everything's in the dark down there, and we need to have good lighting. And of course, the use of computer technology. We'll talk a little bit about creating mosaics and even stereo 3D imagery. So lots of advances, including even using cameras as sensors, and that's really important for the autonomous underwater vehicles that are being built that rely on those camera systems as actual sensors for providing information to the operation of the AUVs.
And we'll talk more about a number of those things tonight. But first, tell us a little bit more about how ocean imagery is collected today and some of its applications.
Sure. Well, we use usually robotic vehicle systems or autonomous vehicle systems. One example is using an ROV such as Jason. This is actually a photo I took the other day of Jason on the Neil Armstrong getting ready to go to the Mid-Atlantic Ridge for an expedition. And it has LED lights, like I mentioned, and it has high quality 4K cameras. And so this is the platform for doing our imaging. And it's one of many different types of platforms. But this one is a remotely operated vehicle system, an ROV, and there's lots of different ROVs out there. That, of course, there's Alvin and autonomous underwater vehicles as well as imaging platforms. And what we can do with these systems is collect really precise data and actually drive the vehicle in a very controlled fashion because it has excellent navigation systems. And we're able to collect imagery that's basically geo-corrected or true to the coordinates, at least the best coordinates you can give it from GPS to ultra short baseline, which is how we track acoustically where the vehicle is on the seafloor. And then that improves the quality of the imagery we collect. And we actually did this on Titanic in 2004. This is the Hercules ROV system. Bob Ballard returned to this site. I was fortunate enough to be there as well, where we did collect this mosaic image of the Titanic. And here's an example of a comparison between the data we collected in 2004 and what was collected in the 1986 expedition. After the discovery, they went back to the Titanic with Alvin. And they used, as Stu was describing, film cameras to actually collect the imagery that had to be developed and actually manually kind of stitched together, looking at overlaps to kind of create, as best they could, a photo mosaic, which again is this 2D representation, in this case, looking in plan view. You can also do photo mosaics in profile view. But this is what we did at the Titanic in 1986. And then in 2004, we digitally used computer programs to stitch the imagery together using some advanced techniques that were developed by Woods Hole engineers, and incredible resolution, processing many more photographs than what was used manually. And in this particular case, you can see incredible resolution. You can zoom in on features and see much more detail than you could in with the old images. So just an incredible difference in the technology for photo mosaics. And we also look to do photogrammetry, which is a really important thing for underwater archaeology and other sciences. Here's an example of a shipwreck that we studied in the Gulf of Mexico, a copper-clad shipwreck. And
Sorry, so what's the difference between a photo mosaic as a bunch of images put together?
Yeah,
What's
right,
photogrammetry?
They're stitched together kind of in a 2D, just to create a 2D representation of the feature that you're imaging, in this case, shipwrecks. And photogrammetry or photogrammatic imagery is a 3D representation of the feature that you're imaging. So that it provides much more detail, a volumetric kind of information, even things that you can measure down there. So part of photogrammetry is the ability to measure features and look at the relative positions of features and look at things in a true 3D representation. So when you process the data, you can make an image like this, and you can actually rotate it around, zoom in and zoom out, and really like pretend you're a scuba diver on the shipwreck virtually, right? So really important for underwater archaeology and other sciences, as we'll see later in the episode. So there is a now emerging field of underwater cultural heritage ecology, and there's a field of biology that's benefiting from shipwrecks because these are artificial reefs. These are objects that are not supposed to be there, and animals can populate these objects and in different ways, and it helps us understand the science of how animals populate a region. And we've introduced an object into the seafloor that actually becomes a reef. And so in this case, sponges can grow on them, and we have other shipwrecks that have anemones and corals and other animals. And Kirsten Meyer-Kaiser is a biologist at Woods Hole Oceanographic Institution who's very interested in studying shipwrecks because of their role as an artificial reef to understand the ecology of the deep sea. And here's an image that Kirsten's team helped produce of the wreck of the Portland, which is on Stellwagen Bank, which is off the coast of Massachusetts, actually. And you can see here it's covered in fishing nets. And so through this photogrammetry or 3D reconstruction of the site, we can glean all sorts of new information that would not otherwise be possible. And really the whole reason why we need to do this is because we don't know what these sites look like. You can't send a camera down and take an image or collect an image or take a photograph of the entire site. So it's so dark down there, light really only penetrates maybe up to 5 meters at the most. And so it's a really interesting for us to create these mosaics and do photogrammatic imaging so that we can understand what these sites look like in their entirety. Unlike on land where you can take photos of really wide areas, we can't do that underwater. Another example of the Titanic bow with an organism that's living off the steel and the iron-eating bacteria forming these animals called rusticles. So a whole science has evolved from the study of shipwrecks, which is quite fascinating.
Yeah, that's fascinating. Victoria, you've been so patient. Introduce yourself a bit to our audience. You're a field roboticist. What kinds of technical challenges do you work on?
Hi, everyone. It's nice to hear all these wonderful stories and hear about all the technology. So I'm a field roboticist, which means I feel obligated to define a robot first. So a robot is this embodied technical system, and it can sense the world, it can interpret those measurements to make sense of the world, and then act in the world according to those measurements. So the specific thing I work on is sense making for a robot brain. So interpreting measurements into a model of the world to then do something with that. And when we're talking about robots in an ocean sense, so we've already heard a little bit about ROV Jason. We're looking at HOV Alvin here. And I also work a lot with the Sentry autonomous underwater vehicle as well. These are all robotic systems, and their intent is to go places that we can't go, be really agile, and bring sensors down with them to collect a bunch of different information. My job, I guess, as a field roboticist is to allow any one of these assets to carry the right sensors to the right place at the right time to collect a useful measurement for science. And I do that by employing classical machine learning methods and artificial intelligence and good old-fashioned data science to get that done.
Okay, so then what kinds of scientific questions are you using the robots to try to answer?
Yeah, so I have been working on a couple different projects in the space of spatiotemporal evolution. So basically the idea that the ocean environment is changing, and we want to quantify that with the types of sensors that we have available. So really tangibly, there are like 2 types of things that I've been working on lately. So one is tracking plumes in the ocean. These are plumes of nutrients or dissolved gases that get formed. And this is talking about scales on the tens to hundreds to thousands of kilometers, and their nature is to waft around. So it's a rather dynamic system. And the other thing I think about is the evolution of the seafloor itself, its shape, and the ecosystem that lives on that seafloor and how it evolves in time. So now we're talking about centimeter or better resolution over timescales of weeks, months, or years. And so this is kind of the space of things.
Okay, so tonight's theme is ocean imaging. How does ocean imaging fit into that robotics and assessing environmental change in time and space?
Yeah, absolutely. I like to think about it in two ways. So one is kind of kind of selfish. It's motivation. So images, as we have seen tonight, are incredibly useful for scientists, and they are a source of data like any other sensor. And robots are a great way of getting sensors to the right places. And we are so motivated to go and use these robots and collect this imagery. And what I think is really exciting about imagery is it's a really non-destructive method of measuring lots of cool things that we care about. So from imagery, without even needing to physically interact with anything, we can be looking at biological questions, geological questions, and then from our physical measurements that we do take, because we take physical measurements of fluids and rocks and biology, we can use this all together to then answer deeper chemistry questions or system questions in general. So I want to use robots to get cameras wherever scientists want to put cameras. But the second thing is that cameras are sensors. And so in my world of algorithmic sense making, imagery is this incredibly useful data source for a robot's brain. So you can think of an image, even just a still image contains tens or hundreds of thousands of pixels. And every pixel is a data point. And these data points encode information like color or field of depth. And if you think about groups of pixels, now we're talking about objects in a scene. And we can start asking questions, or the robot can start asking questions like, well, what am I looking at? Where is that in relation to me? Where am I? And once you can start answering those questions, you can do more and more sophisticated things with your robot. And so my sort of challenge as an engineer here working with imagery is how do we extract all of this really rich information from these images and videos, either for a robot brain or a scientist brain to go and interpret and do something useful with it.
Fascinating. And these beautiful images we've been looking at, I believe were all taken by a camera developed by somebody here at WHOI, the MISO cameras. I think you'll talk more about those. And the scientist is Dan Fornari. So talk more about your own work. What are you doing when you go out in the field, and how do you use the imaging yourself?
Yeah, so you are looking at tons of imagery that we've collected as a team over the last couple of years at a test site called 9 North at the East Pacific Rise. The goal of the team, and this is a collaboration I should mention between tons of different folks, including Dan that you've mentioned here, but also folks at Lehigh University and Scripps and Bergen, WHOI and other places around the world, trying to understand the fundamental processes of hydrothermal systems. So hydrothermalism at a really, really high level, I'm an engineer, so scientists, please correct me if I'm wrong, is basically the process of fluid in the ocean circulating through the crust, getting superheated, coming back up through the crust, carrying all this heat and stuff it's encountered along the way. And then all that stuff either concretizes into these vents or gets ejected into the water column as these plumes. Understanding this process tells us a lot about other things on our planet. So like really fundamentally, it tells us what's going on under the crust. That gives us an implication of what happens at the crust. All this stuff that's getting ejected into the ocean helps set global ocean chemistry. And as we know, the ocean serves a really important role on our planet in sort of managing climate and weather and all of these great things. And really super locally, all this stuff is feeding chemical and biological processes on our seafloor. So it's supporting all of these really unique ecosystems that we have a lot of questions about. All of this work, so what we're using imaging for at the end of the day, is to better understand at a very, very fine resolution how the seafloor is changing while it is undergoing these hydrothermal processes. So we are bringing these meso cameras. You can kind of think about them as really souped up GoPros with special optics and special housings to get them down to the seafloor. And we're using them to take high resolution videos and imagery, turning those into the photogrammetric models that Dwight was just talking about, and then using those models year on year to actually try to quantify changes in volume. Ask questions like, how are animals moving in and out of this system? How has the shape changed? And ultimately, how does that connect to the other measurements we're taking? So if the chemistry changes, do we see changes in the rock? If the amount of stuff coming out of the seafloor changes, can we detect that by seeing how tall the spires grow year on year, or how much they collapse? And so we're trying to connect all these things together to better understand the big processes. What you're seeing on the screen here is a 3D model that we've made of a particular spire that's inhabited by lots of really neat creatures. And these types of models are what we're using to try to understand what is changing from a quantifiable perspective year on year. We can see with our eyes, but how do we put some numbers behind that?
Amazing. Really amazing modeling, and just to be able to see that level of detail is incredible. All right, let's pause here again for some more audience questions. Ken, anything specifically for Dwight or Victoria?
Yes. Especially a couple of people have asked sort of similar questions about this. So as your measurements get more and more precise, and as what you're trying to measure gets finer and finer, how hard is it to position your camera where you want it, either where you're hanging it down or driving it on a vehicle subject to currents? And how does that affect the measurements you can make or the data you can collect?
Well, I can take a crack at that one. Yeah, it's incredibly challenging, certainly with autonomous underwater vehicles, because you're using a pre-programmed vehicle system to go, and you have to use some predictive ideas to assume where it needs to get the best photographs, and you don't have the precise control. But that's unlike a remotely operated vehicle, which actually does have the ability to get in quite close to features and actually get incredible resolution. We can zoom in on things and see, down to centimeter scale resolution. And often we have underwater lasers that are fixed at 10 centimeters, so we can see very precisely what the size of what these animals are, or what these features are that we're collecting images of. And the ROVs are good for that, because we have live control over that ROV and can drive it exactly where we need to. And we know its positioning quite well. The deeper you go, it gets a little bit, the error gets a little bit larger in how accurate you're getting your positioning. But it has a Doppler navigation system on it that gives it incredible relative positioning relative to the seafloor. So even if we're not perfectly accurate with our geographic coordinates, we're very accurate with our seafloor relative positioning. And that allows us to really get down to centimeter scale resolution just on the position of the vehicle. So we can use that when we do our photogrammetry to get pretty accurate and precise measurements. Victoria?
Yeah, I mean, I think it also can't be undersold how important it has been that the cameras themselves have just gotten really good. If you can take really, really high resolution imagery, the images themselves don't necessarily need to be aesthetic to a human's eye to be really useful data. And so the improvement in the resolution and the capabilities of our sensors and our chips inside the cameras is really helpful, and our ability to illuminate things. So Dwight mentioned the LED cameras earlier. I think that our ability to illuminate things further away, to illuminate things so evenly across a scene also helps us a lot when doing this reconstruction work.
All right, we're a little bit behind schedule, so I want to make sure we keep going and hopefully have time for some more audience questions towards the end. We've been talking about imaging technologies and their applications in the deep ocean, but imaging technologies have many other applications in ocean science and beyond. Stu, you ended up leaving WHOI and eventually going back to your first love, aerospace engineering. Give us a sense of the kinds of imaging projects you worked on.
One of the first projects I worked on at UC Berkeley when I came here was building a specialized camera for viewing transient luminous events from in the upper atmosphere. This camera that you see here was built to look at sprites. This instrument was carried aboard on a Taiwanese satellite called Formosat 2. You can vaguely make out in this graphic the camera over on the left-hand wing of the spacecraft. And so sprites are electrical discharges in the ionosphere, and these images that you see here, especially the one on the right, has been colorized. But these are electrical discharges that well up into the ionosphere, and they're associated with lightning down at the ground level, down in our lower atmosphere. They don't happen every time there's a lightning strike, but it happens on certain high energy lightning strikes. And from space, we were able to then map out the global distribution of where these sprites occur as we were being orbited around the Earth on that satellite. One of the other projects I worked on was a project called Themis, and we actually built 5 spacecraft. They were launched all together on one launch vehicle. They were launched in 2007, and they're still operating today. And the mission for Themis was to study the physics of a particular phenomenon known as auroral substorms. And as these satellites orbited the Earth out into the outer reaches of the Earth's magnetic field, there was a network of ground-based observatories that we deployed across Canada and Alaska. And each of these observatories had an all-sky camera looking up to view the aurora. And this image that you're seeing on the screen right now is an example of the mosaics that were produced from the ground-based observatories. And it's overlaid on a map. I don't know if you can make it out. The red background is a map of Alaska and Canada, and you can see there's 6 or 7 images from sites across that region, and showing the aurora occurring in an arc all the way across the continent, basically. So this is a continent-wide image created from a mosaic of many stations, and right in the center there was an example of a breakup of one of these auroral substorms. But of course, this image that you're seeing here is what it looks like from the ground, looking up at these arcs of an auroral display. But our mission was to try to investigate how those actually occur and what's the mechanisms what's causing the aurora. So.
All right. Yeah, we actually got to see the aurora here on Cape Cod over the winter, which is pretty exciting.
Pretty unusual. Yeah.
Pretty unusual. Yeah.
We're right at the solar maximum right now. So.
Yeah. Dwight, you joined WHOI about 6 months ago as our brand new director of ocean imaging. Can you talk a little bit about what that role involves?
Yeah, thanks. WHOI is such a great place to study or work on ocean imaging technologies because there's so many great engineers and scientists that are either developing systems themselves or relying on those systems to do their research. And there's a wealth of ships and technology out there, robotic technology and platforms for these imaging payloads. So I've come in kind of to work with a variety of people in different ways on their technology and try to make improvements and try to bring some a thread of sort of commonality to the way we're doing things for the institution. So one important part of that, of course, is communications, and part of that is education as well. We want to take all the great images that we can collect and share them with the world and share them with the public, and that's really important to our outreach. And there's a great example of that. Recently, there was actually a volcanic eruption underwater that was imaged by the Alvin human-occupied vehicle. And this is just, I think, last week or 2 weeks ago.
Sweet.
Victoria had mentioned the East Pacific Rise and 9 North. So we're actually revisiting that site. It's a very frequently visited site with the Alvin submersible and other systems. And there's lots of scientists that are studying the dynamics here. As you saw in that graphic Victoria showed of a mid-ocean ridge system, this is where new ocean crust is created. And so you can see little flashes of light in the distance there. Amazing footage here that's very rare to collect of an actual eruption happening underwater. So incredibly exciting
Yeah,
footage.
so those little lights are actually the eruption as it's happening, right?
Correct. Yes.
Really incredible.
Magma has risen up to the surface and is erupting as lava, and it's crystallizing as volcanic glass and basaltic rock, and that is forming new ocean crust that these spreading centers are evolving. So this is the process we know about in theory and we've studied with other means, but very rarely do we get to witness it with our own eyes, especially from a platform like Alvin. So incredible, exciting footage there that is meaningful to science, and this is the type of thing we want to work on to even enhance and get higher quality images. You can even see like visibility is really low here. That's because there's so much gas and particulate material in the water. And there's actually WHOI engineers who are working on camera and lighting systems to look through that murkiness actually. So we hope to make improvements in the future, but also have opportunities to collect great footage like this and share it with people.
And I know you're still new, you're still getting your feet under you here at WHOI, but can you give us some examples of the kinds of imaging projects that are going on here? Just very briefly.
Yeah, and some I've learned about very recently since I joined, and others I knew well about. One is a technology for looking in shallower waters at plankton, and there's a piece of technology, a sensor called the IFCB, the Imaging Flow Cytobot, and this is an instrument that pulls water in with a pump, and it's actually able to take thousands of photographs of microscopic organisms that's living in seawater at the surface. And this is plankton by and large, phytoplankton and zooplankton at microscopic scales, and we can actually image them and get their shapes and use AI, artificial intelligence, to actually help identify what some of these animals are, and that's really important to the science. Plankton is the base of the ocean food web, and it's also really important for understanding climate change. And so Heidi Sosik's group, a researcher at Woods Hole Oceanographic, is developed this technology, and it's proliferated around the world with lots of different sensors in the field. So that's one example. There's another.
You said, just a small correction. You said shallow water. I believe it can be used pretty much anywhere, but it's really the surface layer of the ocean.
Yeah, well, phytoplankton,
sunlit layer.
For example, phytoplankton is a plant that relies on sunlight, so it grows in the surface water. So by and large, they're used near the surface waters. And so as we get deeper, actually, Mesobot is a vehicle system that studies the mesophotic zone or the mesopelagic zone, which is the twilight zone, as we call it, which is where very little light can penetrate, but there's still a little bit of light. And there's vertical migrations of animals up through the twilight zone. And Mesobot was a vehicle that was custom built to navigate itself according to the light field. So it could actually collect measurements of how much light there is and follow that as it varies over the course of a day and get all sorts of exciting imagery that is rarely ever imaged before. Most of our imaging systems on vehicles go down to the seafloor to take pictures. Mesobot can hover in the midwater and actually have technology for tracking things and moving according to the light, as I mentioned. So another interesting example. There's others as well. There's a vehicle system called Curie, and this is developed at the Warp Lab by engineer Yogi Girdhar. And Curie studies coral reefs, but other ecosystems in the shallow waters. It's a small robot that is remotely operated, and it's battery operated and can work autonomously, and it can actually collect imagery and be smart enough to identify different features and to guide its path a little bit based on what it's sensing. So it is using those cameras as sensors. In this case, it's following this fish, a barracuda, and it's able to use artificial intelligence and machine learning to adapt how it moves through the water based on what it's sensing in the environment. So really incredible technology that's super important for understanding these marine ecosystems, and certainly coral reefs, which, as we all know, are threatened by climate change and worthy of study with vehicle technology like this. And we need to collect great images to do that. There's a couple of other vehicles that are being worked on. MROVE is an exciting one that I'm part of. This is the medium-sized remotely operated vehicle system. Woods Hole is building 2 of these right now. They're still in their design phase. We're getting close to the construction phase. And so these are smaller vehicles than the Jason, for example, and they'll be able to be transported and more easily operated on smaller ships and with smaller crew, smaller teams of people. And it's a partnership with Green Sea Systems, and we're working to develop remote operations technology so that we can remotely control these vehicles and also remotely operate the technology that's needed to support the vehicles. For example, the imaging systems and the way we record all the data can be all remotely controlled. And so this is an exciting new project that is using advancements in telecommunications and software to basically be almost autonomously used in the field and remotely operated from shore. And there's another project to use to develop an imaging payload for the Remus vehicle. And we hope this gets some traction. We want to put some camera systems on this because it is a workhorse. It's able to map an area with acoustics very effectively. And if we can put good imaging payloads on it, and it has had some imaging payloads on them before, but we can collect data like this, which is acoustic in nature, and then go and have the AUV smart enough to go back and return to some of these targets with their cameras and actually take some photographs using the camera system as well. So this is all important new developments in using camera systems on these sorts of platforms. And then that we hope to actually be able to do collect photogrammetric data as the AUV is surveying some of these sites. If we can get it to go slow enough and the camera to trigger fast enough, we can develop mosaics and photogrammetric reconstructions in real time. So we're looking forward to all these things.
Incredible stuff. We are running out of time, but I want to, first off, I want to give a quick hat tip to Dana Yerger. He's the lead scientist on the Mesobot project. You mentioned Heidi Sosik and Yogi Girdhar, so I just wanted to make sure we mentioned him. He was also the lead engineer for the, let me get it right, the Angus vehicle. Is that right, Stu? Or one of?
No, Dana was really the original father of Jason.
Okay.
Yeah, so he kind of directed the effort in the early days, although he moved away from the actual engineering of the vehicle to more of the control and use of the vehicle. But no, Angus preceded his time at
My mistake. Okay,
no, that's all right.
Abe and Sentry, though, are part of Dana's portfolio.
Okay. Victoria, I want to give you one last question, and I know you're using ocean imaging as part of training the next generation of engineers. Tell us a little about that.
Sure. So I work at Olin College, which is a primarily undergraduate engineering school. And its mission is to really train individuals who are going to be ready to, on cross-functional teams, tackle big, complex, inherently interdisciplinary challenges that we're all facing today and tomorrow and into the future. As part of this mission, we offer a curriculum that's really centered around project-based learning, and that's placing that rigorous textbook knowledge in context with real, authentic challenges in the form of projects. I think ocean imaging is such an exciting way to offer students an opportunity to, learn fundamental concepts in computer vision and computer science and data science and AI, learn some fundamental concepts in physical sciences like environmental science or chemistry, and then also get a chance to work alongside a scientist who cares a lot about the information that we're going to be able to extract from this imagery to advance some real science goal. I think what's really exciting about ocean imaging and ocean exploration in general is it offers so many different types of learning experiences for students. So there's the at sea experience. So I've brought an undergraduate to sea and we've done field work out there doing real image processing to help inform some of the ways we are using assets at sea. So that's a really hands-on project, doing computer science at sea, but also back at home, we are using the real data sets that we collect during these expeditions to train students on the very fundamental algorithms using the science to motivate cool technical challenges. So as we've kind of seen throughout tonight, ocean images or images that are taken underwater are different than the images that we take up here in the air on land. So they are murkier, there's light attenuation stuff going on. We can't just use out-of-the-box algorithms. And so if we want to use this data, we want to create the most accurate models possible, we need to innovate on the algorithms that we actually use. And we can have undergrads doing that today and making a real difference on that frontier of science. And at the end of the day, ocean science in general is basically doing the impossible with teams of people from many different expertise fields and experiences, and getting to put an undergraduate in that intellectual community is really exciting. And they'll get to learn all these tools and skills and carry that with them wherever they go to solve these big challenges in the future.
I wish we had another 3 hours to keep all these great conversations going, but I'm afraid that's all we have time for tonight. But stay with us, audience, for that special presentation I mentioned earlier, the original footage and audio from the discovery of the Titanic that you heard Stu talking about earlier. But first, I want to say, yes.
Yeah, I just wanted to say, having worked on underwater imaging systems 40 years ago, it's really remarkable to see what people like Dwight and Victoria are doing these days with underwater lighting and cameras, because the physics of underwater imaging haven't changed, but the technology definitely clearly has.
Thanks, Stu. Yeah.
All right. That's a great closing comment. And I want to say a big, big thank you to Dwight Coleman, Victoria Preston, and Stewart Harris for joining us to talk about imaging technology in the deep ocean and beyond. Thank you all so much for a really special show tonight.
Thanks for having me.
Thank you.
And thank you also to my WHOI colleagues who have been working very hard behind the scenes to make this event possible. And to everyone who joined us on Zoom, Facebook, and YouTube, thank you. Tonight's event was the season finale of our 7th season of WHOI's Ocean Encounters events. Our next season will start early in 2026, so please watch our website, whoi.edu, for more details about that. In the meantime, you might want to take a look at the very cool merchandise at WHOI's online store, shop.whoi.edu. You get a 10% event discount for joining us tonight. Just type in the discount code IMAGING. If you enjoyed tonight's Ocean Encounters program, you can be part of WHOI's solution-based approach to ocean science. If you're already a WHOI member, thank you very much. As you know, a benefit of WHOI membership is receiving our award-winning Oceanus member magazine. If you're not yet a WHOI member, please consider joining so you'll never miss an issue. You'll get other great benefits too, and you'll be providing crucial support for our outreach and our science. Memberships start at just $40 a year. The average gift is $120, but any amount helps. If you do become a member, let us know that you watch Ocean Encounters. That will help us keep bringing you the science programming you enjoy. On behalf of Woods Hole Oceanographic Institution, thank you and good night.
What is that gizmo? I'd love to get that. Something big off to the right.
I know. It's starting to burn in. Oh, look at that. Look at that. Somebody should get Bob.
It was quiet as a mouse, but Emory woke up too. I don't want to be
It's okay.
Somebody ought to go get Bob.
Where is he?
Yes.
Call the bridge.
Yeah, call the bridge.
Down and get him. I know where he is. Okay.
Oh, I love it. I love it. Still plenty of jump
This
coming.
is it.
Still plenty of
Look
jump.
at
That
that
was
thing.
something that you could see.
It was a great big box with a hole in it.
That was a commode, baby. Look at that.
We realized
I know. Look at it. Whoa!
What? What is it?
I don't know, but
look
it's
at it.
man-made.
It ain't no geology.
Let's see. That's
Good.
Okay.
04,
Oh, well. Okay. Forward. More stuff coming.
I know.
Hope we don't find anything too big.
I don't know. It's awful heavy up in front of us, that's all I can tell you.
That is big.
Look at it. What the hell? Oh, God, it looks like a boiler.
A boiler.
It looks like a boiler.
Yes, yes.
Fantastic. All right.
Shit, we're gonna nail this too. I'm switching now, Bob.
Excuse my enthusiasm.
Oh yes, I'm sure it's a boiler. I see. Yes.
Okay, I better get this thing plotted.
We
I
got
noticed
it.
what we're doing at 2:30. Billy said
I'm
so.
starting to really burn up.
Billy said 2:30.
It's all over. There's massive iron below us.